Okay. Dear colleagues, let me present to you the result of our work with the title, I am Evgen Burov from Polytechnic National University. And the theme of our work presentation today is the route selection method on military information and telecommunication networks based on use of ANFIS. Let me share my screen with you. I hope you see my screen. And this is the result of common work of National Hetman Petro Sagaidachny Army Academy and Lviv Polytechnic National University. The problem we address in our research here is the prediction of routes in military information and telecommunication networks. Basically, military networks use the same technology as our civilian networks, but they have a lot of more stringent requirements as to quality and reliability of services. In our current setting, telecommunication networks use routing protocols and reliability indexes based on the states of adjacent nodes, adjacent routers in a computer network. In our work, we propose a method which will use historical information about different kinds of failures in the network to predict and therefore update the reliability indexes in the routing algorithm using in information networks, in military information networks. This algorithm is based in ANFIS, which is an adaptive neurofuzzy inference system. This ANFIS system can be represented as black box. In the input of this black box, we have several input values like x1, xn, and the output we have y values. So it was basically approximation of functional dependency. And typically, the ANFIS network has a several layer. As neural network, it have input layer of several values, output layer, and conditions part, if part, rule parts, normalization, and decision-making then part, and everything is summarized in the output layer. This is a typical structure of ANFIS approach. We have developed a route selection method based in following steps. In the first step, we determine the failure classes, the K failure classes of routers in the computer network. Next, we implement the ANFIS network for each node and for each failure class. In the first step, we should determine the ANFIS architecture according to the method, the main stage of which include determining the number and type of input values, number and form of membership functions for each input value, the number of layers of fuzzy neural network. Next, when we already have such ANFIS network, we will need to train this ANFIS network based on statistics collected for previous period for specific failure classes. Next, we predict the values of a number of values of Kate class in the nearest time interval. And we need to calculate the overall reliability index of node according to this conversion into the reliability index on the corresponding dynamic routing protocol. And next is the calculating the route metric according to the rules defined by dynamic routing protocol and updating routing tables. This is 8 steps of our algorithm. In this slide, you see the segment of network used to calculate those metrics. or reliability indexes, you see that in each node of this network, you have a number of ANFIS decision-making neuron networks, fuzzy neural networks, which allow us calculate the reliability index M1, M2, and so on for each pass. And in order to use in practice our developed algorithm, we need to map the obtained predicted reliability index Rj to the existing gradation of reliability indexes, for example, of typical of popular IEGRP protocol. In this table, you see such mapping between predicted reliability indexes and they use the EGRP reliability indexes. In this slide, you see that the representation of synthesizes and ANFIS structure. In our experiment, we used the values of flow of each. You know that we have a k different types of flows, and for specific kind of flow, we used the values of this value of this probability, this flow in 4 previous moments of time as an input, and we calculate the value of the probability, the reliability index in the next moment of time using the values of 4 previous time moments observed. In this slide, you see the form of membership functions, mu, as represented in this slide, obtained as a result of training of our ANFIS network. And this based model, we trained it using 5,000 different values, and it was trained in MATLAB. The initial assumption was that the failure rates for each K class was random and uniformly distributed. And as a result of our training and subsequent testing of this model, we obtained that the accuracy of predicting the value of failure rate is like 94–96%. So this work will be without doubt continued and development, taking in consideration maybe other parameters of other failure cases for routers or in networks. This is all for me. Do you have any questions?
Thank you very much, Professor Guru. Any questions?
Yes, may I ask a question?
Please, Dr. Lesky.
Please, questions.
Well, I would like to know more than the report. I would like to know more about your input data. The
Please,
data
microphone.
natural language data.
I have
The prepared. Do you hear me?
Okay, maybe I didn't quite follow your questions. Maybe you
Prepared other raw data obtained by different operators. Or they
the data were randomly generated in
Dr. Far from your mouse.
The data were randomly generated and uniform distributed, and they were split into subsets of data. One of subsets was used train the model, and another was used for testing.
Thank you.
Maybe other questions for me.
Any other questions? No questions. Yeah. Thank you very much for your report.
Okay,
Then
thank you very much for
next
having me.
speaker, Julian Kuruliak.
Okay, stop share.
Hello.
Please, thank you.
Hello, dear audience. Topic of our presentation is the effect of complex network topology in managing epidemic outbreaks. First of all, I will talk about epidemiology, then I will move into complex network, then to simulation method, and finally I will talk about studies. Prediction of the dynamics of the spread of the infection disease in society is an important problem, especially in present pandemic conditions. The main task is to restrain the disease spread until the population is immunized, and to stretch it over time to reduce the load on the hospitals. Our goal is to study the effect of network topology on the disease spread rate. We focus on the peak number of infected. This is critical indicator for the epidemic, and the hospital load depends on it. In epidemiology, there are usually three main states in which the nodes may be in process of simulation. There are susceptible, infected, and removed. Removed means immunized or dead person. There are three main epidemiological models. There are SI model, which assumes that infected not forever be contagious. There are SIS model, which assumes that the node after treatment again becomes to susceptible state and can be infected again. And also SIR model, which involves removing the similarity. We use SIR model because it's more closest to COVID-19. Classical epidemiology has mainly focused on homogeneous network structures, such as complete networks with the same number of contact per network, and also not in it. And also in real networks, areas with high and low networks presented and not person, and degree is a contact. Is a zero model of network in epidemic. In this graph, all nodes are interconnected. Model is not real, but it may be part of network. This part called click. In it, virus spreads very fast, and the result not realistic enough. The Erdős model is a random network because all edges connected random nodes. This model often used when talking about average number of contacts per person. What-Stroger's model is designed to demonstrate a small word, as in the example of 6 handshakes. For at start is a regular graph, and then each of edges has a probability reconnection. The Barabási-Albert model is a free-scale network. This model have hubs so it is closest to real networks, including social ones. The distribution of degrees in scale-free networks is described by power law distribution with gamma equals 3. The simulation, for the simulation, we use a stochastic Gillespie algorithm, which uses continuous time Markov chains. Probability of infection of node depending on number of contacts of the node with infected nodes, and time to next infection depends on the total number of contacts with infected nodes in network. Our parameters is network model, size of the model, amount of initial edges, infection rate, demographic distribution. We use demographic distribution of Ukraine from 2020, and also distribution of critically infection probability. We use mortality data from COVID-19 in Ukraine increased by 0.2. Term of spread of the disease, we use 10 days, and period of spread the disease by critically infected person, it is 14 days. Study of the influence of individual and weighted probability of critically infection. It was our first experiments, and it displays the importance of the individual probability of critical infection. To compare individual and weighted values, we use a complete graph with 200 of nodes and median values from 36 simulation for each case. The individual probability of critical infection has less than critically infected nodes than for the weighted probability. To study the importance topology, we use 3 standard network models with a similar average node degree, and compared them with a complete graph, because complete graph often used in classic epidemiology. In the table, you can see properties of the network. On the figure, you can see the dynamics of the virus and in this network. The Barabási-Albert model has highest rate of disease spread, so highest number of simultaneously infected too. Slightly lower values are in Erdős-Rényi model and the lowest in Watts-Strogers model. Here we concentrated on the peak number of simultaneously infected nodes in the network for different infection rates. From this experiment, we conclude that the rate of disease spread in the network and also peak of infected depends on the average shortest path length. We compared the Erdős-Rényi and Barabási-Albert models because they have similar values of average shortest path length, but the values of clustering coefficient are different. You can see properties on the table. Another reason was that people often talk about average number of contacts per person, and in this case use Erdős-Rényi model. We compare it with Barabási-Albert model, sorry, which is closer to real network. Here you can see a number of peak simultaneously infected for different infected rates in linear and logical scale. The Barabási-Albert model has higher clustering coefficient, but the difference in the peak number of simultaneously infected is not big if don't take into account the asymptotes of the Erdős-Rényi model like this. because not one given cluster. Therefore, clustering coefficient has little effect on the number of simultaneously infected. As in conclusion, a study of a virus spread in different networks topology shows that the average shortest path length has greatest influence on the dynamic of the disease spread and on the number of simultaneously infected, while the clustering coefficient has a little effect. As an example of a social network avoiding two crowds of people, the clustering coefficient of a network will be significantly lower, but it is more important to minimize contact of or immunize people with large number of contacts, such as bus drivers or cashiers. This will reduce the average shortest path length. If you have any question, I can answer them.
May I ask a question?
Yes.
Well, thank you for the report. Now there is a very popular idea of using the similar approach like here and something like this to use it in social networks for studying, for using. Do you hear me?
Yes, I hear you.
Idea of using such an approach for social networks to study how different ideas or information influences are being propagated through social networks. Didn't you think about such a research?
About information spreading in social networks, yes?
Yes, information influences ideas.
We didn't think about it, but in this model, we can do it. It is continuous time Markov chains with Gillespie algorithm, and we can simulate it, but it needs parameter like infection rate. Yes, we have infection rate for disease, but for information, we have something like probability of sharing this information. So we can use it in this.
Thank you.
Thank you for the question.
Thank you very much. Any other questions? No questions. Thank you, Kurilyak. And next report, Vasilenko.
Okay, thank you.
Please.
Take care about yourself and others. Thank you for attention.
Thank you.
And share your screen. Yes.
Yeah. So dear participants of MoMLeT's workshop, let me present you my work, which is called Knowledge Representation and Automated Formal Reasoning in Description Logics ALC. So let's start with the introduction. So we have a really complex world, and modern ontologies tend to grow in size and in their complexity. And we need to have some kind of a tool that would allow us to describe the modern complex world. And speaking about languages that we have for description, we know that we have OL2. And those languages like OL2, they can be characterized by expressiveness, so how much they can represent from the real world. Other than that, each update or extension to our ontology can disrupt the logical consistency, so we can introduce two contradictory statements, for instance. And if you want to avoid that, we would need to have some kind of a procedure that would allow us to check the logical consistency. And what's more important, that procedure should be tractable or at least decidable. So the termination problem should not exist there. There is a fundamental trade-off. Speaking about expressiveness, is the notion that is defined like the more constructors a language has, the greater variety of ideas it can represent. And we have another option called undecidability. It's from the theory of algorithms. It means that it's impossible to construct an algorithm that always leads to a correct answer for certain problems. And that's the other name for this problem is a termination problem or halting problem. In 1987, fundamental trade-off researched by Levesky and Breckman, and to be concise, it means the higher expressiveness of a language leads to understandability of reasoning problems. So the can express the more possibilities that we would not be able to automate the solution of reasoning problems. So how to ensure logical consistency of the modern ontologies? I would propose an answer like formal reasoning using description logics. For formal reasoning, it's a technique, and it consists in syntactic transformations which are applied according to the rules and axioms of formal system with two purposes: derive a new expression from the given context or verify the consistency of a given and existing expressions. So here on the slide, you can see statements from the formal systems. The first one belongs to the first order logic, the second one belongs to the type theory, and the third one is an expression from the description logics. So description logic are basically are subsets or decidable fragments of first order logic, and they form the basis for all two and all language. It has the following ontological commitments. There are concepts, individuals, roles. So concepts represent the entities in the domain of interest. Individuals are the instances of domain concepts, and roles are the relations between concepts. And we have like two structural parts of our knowledge base: terminological part and assertional part. And those two pieces form the knowledge base. In description logic LC, each concept name is a concept description. So each name that we can introduce is a concept description. Top and bottom types are also concept descriptions. And there are some possibility of construction of the following compound descriptions. For instance, we can create a conjunction of concepts, union of concepts, negation of concept, existential restriction, and values restriction. ALC is basically deciphered as an attributive language with complements, and it allows us to describe concepts and the relations between them and provides this set of operators. Speaking about its semantics, the semantics for description logics is an interpretation where we have an interpretation domain and a mapping that maps each concept name to a set and each binary relation to a set of pairs. So it's very common to the model theory. And as you can see, for compound components, we have also defined formal semantics, and it's very similar to what we have in model theory. Is basically the ones that operate with the sets and their operations. Other than that, we can also state a useful lemmas based on the description of the operations that are allowed in LC. And those lemmas are very similar to the ones that are present in first order logic. And we can use them during the reasoning process. Here is an example of domain modeling. So if you want to model a domain IT project structure using the description logic and in the context of a project smart city, we would have the following domain. The first thing that we need to do is to define the concepts that we are interested in, and then we need to specify their interpretation. For instance, we have like the whole interpretation domain consists of the following objects, and each concept has also its extension provided. And that interpretation can be visualized in the form of oriented graph, where all the interpretation elements correspond to the vertex, and their labels are basically the concepts to which they can belong. And on the edges, we can see the roles that connect those elements from interpretation domain. Other than that, a concept of knowledge base, and as you can see, it has two parts: terminological box and declarative box. In terminological box, we have a general concept inclusions, so it's like concept definitions. So there are two operations that allow out its concept inclusion and concept equivalence. And in a box, we have like a set, it's like more precise, more detailed description of knowledge base. We have a possibility to create an element of some of concept and a role assertion as well. For instance, here is, if you want to create a knowledge base for a T project structure, we can like have a T box that will consist of those two items, like technology is method and tools. And for instance, engineering is equivalent to human and has a skill of a technology. And below three statements belong to a box where we have an instances of that concepts, like Mary is an engineer, UML is technology, Mary of UML. In order to do the reasoning, we need to define the model of knowledge base. So a model of knowledge base is basically an interpretation that satisfies all the statements in knowledge base. Model of T is, it satisfies all the statements in T box. Model of A satisfies all the statements in A box. And if model satisfy all the statements of K, then it's a model of our knowledge base. Based on that, we can, based on the descriptions that are allowed in LC, we can specify the following reasoning problems. So we can specify the reasoning problem of satisfaction, whether C is satisfied with respect to T. It means that concept C is not empty in that interpretation. Whether C is included in concept D, whether C is equivalent to D, whether K is consistent. And whether B is an instance of concept C. So we will be interested in the problem which is called K is consistent, so the consistency of knowledge base. There are the following reasoning principles that we will use. The first one, and potentially the most important, is that T box can be unfolded into A box by recursive replacement of all concept names in A box with their definitions from T box. Other than that, all the basic problems of LC, so those that we specify here, can be reduced to the problem of knowledge-based consistency. So if we will have an algorithm for knowledge-based consistency, we can solve the other problems. And the idea of a Tableaux algorithm that we are going to use is to construct a model of K using unfolding rules. So if we can construct a model for knowledge base, then it means that it will be consistent. Tableaux algorithm has the following rules. So it has unfolding rules for LC box consistency. So for instance, if we have the following statement like A belongs to the concept C and D, and the following condition applies, so there is no A of C and A of D, then it means that we can extend our A box with two new statements like A belongs to concept C and A belongs to concept D. So we basically break that compound description into simpler ones. We also have as axioms for acyclic LCT box, and we have an axioms for general knowledge base. So you know that there is a possibility of circularity in dictionaries. So just to avoid the circularity, we are introducing a concept of blocking or not blocking. But let's see how it works on a problem. So for instance, we have a knowledge base related to the domain of mass media, and we want to check whether it's consistent using the Tableaux algorithm. So we have an example of news has author is either human, organization, or bot. Bot is not human and also has an author, and organization, it has humans. And we have that term, a box where A is news, A and B are related with the role has. B is a bot. B is basically created by organization, and organizations is C. And here's an example of reasoning. The first step, what we're going to do is T-box normalization. We would need to simplify our statements and normalize T-box. And then we can apply our rules that are specified here. So we just need to select a rule and a statement that's possible to be applied that rule to, and just to do that. So once we'll apply our inclusion rules, we would have 3 new statements in our A box. So those elements will be processed, and we would have 3 new elements here. Then if we will apply our existential rule, we will have 2 new statements. And once we will apply the rest of the rules like and universality restriction, we would have like our even more rules. And when we will try to search for some additional rules that can be applied, there would be no more rules that will satisfy their conditions. And that means that we constructed a model. It doesn't has a conflicts, and that model and the existence of that model proves that our knowledge base is consistent. So here's a result of what we found. We found all the statements that we have in our A box. We can model as an interpretation, and we can visualize that interpretation as follows. And since we have a model, knowledge base is consistent. So conclusions. Description logics are describable fragments of first-order logic with the limited expressiveness. It always will be limited, otherwise we will have the problem of termination of algorithm. Tableaux algorithms provide a method of automated reasoning in description logic-based ontologies. The benefits of automated reasoning are especially noticeable on large and complex knowledge bases. And speaking about OWL 2, description logic through D forms the basis for that logic, and ALC is the basic of that more complex logic through D. Thank you for your attention. If you have any questions, I would be happy to answer.
Thank you, Dr. Rudenko. Some questions. I have one question for you. Is it not enough existing reasoners to automated check the disability? Do you understand what I'm asking?
So there are already Hermit.
I know about Hermit, for example, Hermit.
You can use Hermit.
Tableau approach to check disability. Is it
the whole idea is basically
good or something wrong with this reasoner?
Yeah, I understand the question. So I would say it's currently it's a top reasoners that you can use.
Are you hearing me?
There are some alternatives. Yeah, I can hear you. Can you hear me?
No, we not hear to you, Dr.
How about now? I can hear myself.
Maybe your microphone is closed.
Does anyone else hear me?
No, we hear both of you.
Okay, so okay, I will just try to answer the question because it looks like there is a problem. I would say that it's very important to understand how description logics do work, because the complexity of our world raises. We would definitely need to introduce some additional tools that would allow us to reason about even more complex items, and that's
20 seconds. 20 seconds.
Yeah, and that's why we need to understand how does it work and how can we extend. So when I believe there would be still new description logics that will be implemented in years' time, because it's a constant progress of
interruption to 12 o'clock.